Hello friends, welcome to ChemiCuss. Today I am going to discuss one important topic, that is 1,3-dipolar cycloaddition. So in this video, at first I will spend few minutes on the basic idea of this 1,3-dipolar cycloaddition, and then I will discuss a good amount of examples, because from exam point of view this 1,3-dipolar cycloaddition is very important, and that's why I thought that I will discuss more amount of examples so that you will be familiar with different type of examples that can come or that came previously in different type of competitive examination. Okay, so first I will tell why this 1,3-dipolar cycloaddition is important. So you all know that in the reaction of 2+2 cycloaddition reaction we can get 4-membered cyclic compound, and in case of Diels-Solder we can get 6-membered cyclic compound. But how we can get one 5-membered compound? Either by this 2+2 or this 4+2 cycloaddition we cannot get this 5-member ring. We will end up getting this 2-member or 6-member ring. So to get this 5-membered ring containing compound, this 1,3-dipolar cycloaddition reaction comes into picture. First I will tell some terminology, then I will tell that how this reaction goes on, then I will discuss about the examples. So in case of this 4+2 cycloaddition, this Diels-Solder, we know these two moieties are there. One is called diene, having this 4 pi electron system, and one is called dienophile, having 2 pi electron system. Now in the case of 1,3-dipolar cycloaddition, this diene is diene type of molecule. Like within few minutes I will discuss that what are the two parts of this 1,3-dipolar cycloaddition reaction, because in 1,3-dipolar cycloadditions also we have two compounds, like two components. Like this 4+2 cycloaddition, one part is diene and another part is dienophile. So in 1,3-dipolar cycloaddition also the component having this 4 pi electron system, that is called dipole, and 2 pi electron system, that is called dipolarophile. So you need to know this terminology. Now I will tell the examples that are widely used in this 1,3-dipolar cycloaddition reaction as reagents. So here now I am writing the dipole, and here I will write the dipolarophile. So in case of dipole, the examples can be it will be this one, or it can be it will be CH2 bond. So this type of compounds will be called dipole, 1,3 dipole. And dipolar file generally alkene or alkyne type of compounds. If you write here substituent, so these type of compounds are called as dipolarified. Now in this case you can see this, if I write here 1 2, so this is 1 2 dipole. Why dipole? Because one positive charge is there, another negative charge is there. So you may think that this is 1 2 dipole, then how it is I am calling this as 1,3 dipole. Now if you think like one nucleophile is there, so it cannot attack to this nitrogen center because it is already tetra-coordinated. So we can write this 1 2 dipolar system as this double bonded electron will shift to this nitrogen center and the positive charge will be generated here. Now nucleophile can attack to this center. Now you can see this is 1, this is 2, this is 3. So in this conformation reaction can take place. That's why all this type of system are called 1,3 dipole, not 1 2 dipole. And depending on the nature of this dipolarified, this 1,3 dipole can act as electrophile or nucleophile. So it can act as both electrophile and nucleophile. So in question regarding this 1,3 dipolar cycloaddition reaction, so they can ask that 1,3 dipole can act as electrophile or nucleophile or both. So in that case you have to write they can act electrophile as well as nucleophile. This is the difference with this diene in case of Diels-Alder reaction. In Diels-Alder reaction, the diene can act as only nucleophile. But here this 1,3 dipole can act as electrophile as well as nucleophile. So this is the difference. Now I will discuss a little bit about the mechanism, how it is going on, and then I will spend more time about the examples part. That's why I can recommend to all of you that you watch this video till the end, because from exam point of view this is very important. So I will recommend that you don't miss any like single seconds of this video, so that you can miss some important point. And I will discuss the stereochemistry part also, so that that type of examples will be very much useful for you people. So watch till the end. Now suppose I have this dipolarified sorry 1,3 dipole, and I have this dipolarified. So I am assuming that this is electron rich system. This dipolarified, this R group is electron rich system. So in that case what will happen, this negative charge will attack to this center, because this if I write this double bond like this, positive and negative, see you all can see this positive charge will be stabilized by this substituent, and this is 1 degree carbon ion, so it is also stable. So this conformation will be stabilized. But if I write the other conformation, in that case this will not be favorable. So this double bond, we can imagine it will behave like this conformation. So negative charge will attack here, and this bond will attack here, and this nitrogen center will be stabilized. So what we will get? The product will get this 5-member cyclic compound we will get. Now suppose same 1,3 dipole I am using, and now I have this electron like keto group is substituent like 1,3 alpha beta unsaturated ketone as a dipolar file I have. So in that case, this double bond will be in conjugation with this CO group. So here positive charge, or either you can say del positive charge will be created to this carbon center, and del negative charge will be created to this carbon center. So negative charge again, it will attack this carbon center, and this double bond will attack here. It will go here. So in this case, what will be the product? The product will be this. So you can say in between these two, the conformation, like the position of the substituent is different. So by using this dipole and dipolar file, you can get different type of products. And here this is 4 electron component, and this is 2 electron component. Here also this is 2 electron component, and this is 4 electron components. Okay, now I will discuss some practice question. In exam, what will happen? They will not give directly the this dipolar file and this 1,3 dipole, but they will give some reaction. From that you have to generate that dipole, and they will give some dipolar file. So that reaction you all know, but how to get that 1,3 dipole, then you have to know that part. They will not give directly the dipole 1,3 dipole. So suppose I have this aldehyde. So in presence of this condition, what will be A? So this reagent will be used to generate the 1,3 dipole. So I have this aldehyde in presence of hydroxylamine. You all know this oxime will be generated. Now what will happen? Chlorine is present, so this lone pair will come here, and this bond will attack on chlorine center, and another will go out. So what we will get? We will get this one. Okay, then what will happen? This bond will be shifted here, and this oxygen will be neutralized. So one proton will go out. We will get which? Now triethylamine base is present. So what will happen? It will abstract one proton. So we will get this one. Now nitrogen has lone pair. It will come here, and this chlorine will go out. So in this way we got our 1,3 dipole. We can write this one again like this. So this positive charge will be generated at this carbon center and nitrogen will be neutralized. Now, so this is A and this dichlorophyll is present. So the same reaction will take place. This will attack here and this bond will go here. So we will get this product. And here you can see I have not mentioned the stereochemistry. Now I will discuss little bit about the stereochemistry or the position of this substituent. Okay, suppose again I am taking the same 1,3 dipole and if I use this dichlorophyll having both substituent in the same direction, that means this is cis. The substituents are cis to each other. So that time the product that we will get, that will be cis to each other. So remember this, when the substituents are cis in the reactant also, in product also they will be in cis position. And suppose they are trans to each other, that time in product also they will be in trans to each other. So this thing keep in mind. Now suppose I have this same 1,3 dipole, but I have terminal alkyne as my dipolar. So I have already discussed that this dipolar can be alkene or alkyne, anything. So here I have this alkyne as my dipolar. So the same reaction will take place. It will attack here and this bond will attack here. So nitrogen will be neutralized. So we will get this product we will get. It is called isoxazole. Okay, it is aromatic in nature because these 2 pi 2 pi 4 pi electrons and one lone pair is there of oxygen, so it is aromatic in nature. Now suppose I have this 5-membered compound and they can extend this product using some other reagents. So they can extend the question and they can give like some different reagent and they can ask what will be the product. So suppose this is the product after 1,3 cycloaddition, and if H2Ni is used, this is reducing agent, so that time this weak bond will be cleaved and we will get this one. And if we use lithium aluminum hydride, so that time hydride will attack to this center and nitrogen will be negative in charge, and then after hydrolysis we will get this product. So here you can say I didn't mention about the stereochemistry, but suppose in question you get this product after 1,3 cycloaddition, and then they give this reagent, and after hydrolysis they are asking what will be the product. So you all know that after hydrolysis what we will get, we will get this product, because this position will not be changed, stereochemistry will be fixed. But in answer they can give this answer. So remember one thing, that if in starting material both substituents are cis to each other, so in product also this OH and this one of the substituent that is not connected to the, like the substituent that is connected to the adjacent carbon of this hydroxyl moiety, so they both will be cis to each other. And if these two R group are trans to each other in reactant, so that time in product they will be in trans to each other. So how we can get this, like how we can write this product as like this. So if we write here, if I write here this hydrogen, so you all know that in stereochemistry we can rotate this CC sigma bond by keeping this portion fixed. We can rotate this whole moiety. So if we rotate this whole moiety by anti-clockwise direction, so that time you will get this OH will come to the above of the plane of the paper, this R will go to the plane of the paper, and this hydrogen will remain as it is below the plane of the paper. So these two are identical molecule, so no need to worry. If you have some basic idea about stereochemistry, so that time you can like rotate the single bond and you can get the proper answer. Now I'll discuss some another example. Sorry, this will be hydrogen. Now suppose this question is given, so they are asking this starting material is there, in panes of heat what will be the product A, and if we treat with zinc HOSC what will be the product B. Now by seeing this molecule, here you can see 1,3 dipole is there and this alkene is present, so this will act as diprophile and heat is given. So in presence of heat this 1,3 dipolar cycloaddition will take place. So now we can write this molecule as like this. So we can write this starting material as like this. So then 1,3 dipolar cycloaddition will take place. This negative charge will attack to this carbon center and this double bond will attack here and this nitrogen will be neutralized. So what will be our product? So our product will be So this will be our product. Now if we treat this compound is with zinc and HOSE, then this weak NO bond will be clipped, and what will be the product? The product will be this wedge. Now I will discuss another important example. In that case, the stereochemistry will come into picture. So I am writing the 1,3 dipole, that is this one, and this dipolar file is given. So what will be the product? So if we write again, and if we write this dipolar file like this, so here you can see this is least hindered approach, because this R group is in now is exo position. If this R group is this side, so that time it is called endo approach, but here this is R group is in exo position, so it is more favored approach, because this is least hindered approach when R is in exo position, so it is favorable approach. Okay, so what will happen? This negative charge will attack here, and this bond will attack here, and this nitrogen will be neutralized. So as here R is exo in position and this bond is attacking this side, so this hydrogen will come to above the plane of the paper, as well as the R group also will come to above the plane of the paper. So the product will be so this will be the product. This is a very important example. So again, if we treat with zinc HOSE, that time we will get this product. So this will be the product. So in this video I have discussed the basic of these 1,3 dipolar cycloadditions, as well as I have discussed a good amount of this example part. And this 1,3 dipolar cycloaddition, again I have been saying, is very important from exam point of view. So I will recommend to all of you to go through this 1,3 dipolar cycloaddition in detail, and here I have tried to explain all the things in detail. So I think this video will be helpful for you people, and if you want to know more about this 1,3 dipolar cycloaddition, so you can go through different renowned books. So with this I want to stop this this video here, and if you find this video helpful, please subscribe to our channel and please share with your friends, and thank you for watching.